All right, Yuri, take it away.
Thank you so much. And yeah, I don't have slides. Just going to freestyle it. Yeah, Allison suggested initially picking a topic that you want others to solve. And then when we're discussing like what to put in the tech tree, you can put something that you're working on. And I'm working on partial reprogramming, and one of the things that we're trying to solve is decoupling rejuvenation from loss of cell identity, from dedifferentiation. And this is like one of the biggest risks of partial reprogramming, because the Yamanaka factors are way too powerful and originally were designed to cause dedifferentiation, to cause the loss of cell identity. But of course, in vivo, you want to avoid that. So if you guys want to talk about that, I mean, I'm all for it. And this is the tech tree slide that I'm going to contribute. That if you guys want to like chat afterwards or email me, happy to talk about that. I'm sure Joe will have some ideas about that as well. But since this is like a theme of challenges you want other people to solve, I'm just going to talk about something different that I think is a very interesting question when it comes to, actually dovetails really well with Vadim's topic of what is aging and what is rejuvenation, what are we trying to solve? And to me, I mean, I've been thinking about this for a long time, and as Vadim rightfully pointed out, I'm more of a programmed aging kind of guy. And of course, like for me personally, what we're after is lifespan extension, life increase, and hopefully increase of the healthy years, right? We want, and we'll know it when we see it. When you show us a 60-year-old who's as healthy as a 30-year-old, we'll know, like, this is it. Like, we don't need to study their mortality curve or anything else. We'll know this is the result that we're going to live with. But in terms of figuring out what actually causes these changes that we see, these changes in life stage program, to me it's very interesting that we still don't know the genes or the genetic mechanisms responsible between what actually makes a mouse mature in 3 weeks and a human mature, like sexually mature at 10, 11, 12 years old. And can we actually nail down the genetic mechanisms? Because I think that will greatly inform our understanding of aging processes. And definitely, we can decouple the developmental program from what we see in aging, and there's ongoing debate: is aging a shadow of the developmental program? Is it just completely random accumulation of the damage that is not connected? But I think there is very interesting evidence that there is a relationship, at least between like when development, sexual maturity development starts and the remaining lifespan. And conversely, the relationship when you actually slow down the development or prevent the development, as in some species, they can choose not to sexually mature, and then they actually live much longer. So there's definitely some coupling between these mechanisms. And some people say that sexual maturity turns on aging. And I know Vadim will smile in return, because he's been debating about that and actually believes that aging starts in the womb, is accumulation of damage. And I think this is a very interesting research area that we definitely need more attention on. And in terms of, but figuring out the gene mechanisms, can we pinpoint the genes between organisms that maybe there's a small subset that if we manipulate those genes, we can say get a mouse to sexually mature in a much longer period, instead of 3 to 6 weeks, maybe give it 3 to 6 months. And will that result in a much increased lifespan, or are those actually decoupled things? And to me, this is interesting because like in progeric mice who live much less than normal mice, their actual sexual maturity is about the same. Their developmental program is not affected. So there's an interesting question about coupling or decoupling in early life and in later life. And I think the field of aging hasn't spent enough effort investigating this aspect of like, why aren't we studying the genes that are different between organisms and what makes basically organisms, what is responsible for the development program stages. And I mean, nobody will, I think, argue that those are programmed and there is some sort of circadian clock or some sort of clock that makes everybody start the life stages at a precise time point between species. But we still don't know, like, what are the genes? How is it encoded? Because it's obviously encoded in the DNA, and lifespan is a trait that's somewhere in the DNA, but we still don't know where. And to me, this would be a very interesting challenge to address, to actually investigate. Like, can we at least pinpoint some areas in the genomes that are responsible? And then if we do, can we try to start playing around and modulating that and hopefully getting either a yes answer or no answer about the connection between development and aging. So to me, this is a challenge that you kind of throw out to the ether and hope someone else solves it while you work on something that you're a little more familiar with. So thank you for that. And if you guys have any questions, or maybe you actually know some research that's been ongoing, I'd love to hear about it. Sure.
Just a quick thought that may break it down a little bit further. Does anyone know how fast a naked mole rat develops? Is it 3 weeks or is it later? Because that's a little bit closer than that could be.
Well, they have a caste system, right? They have breeders, and actually, if the queen dies, the workers can actually, one of the workers can, there's like a big fight who gets to become a breeder. So, but in terms of like when they're eligible to sexually mature, I wish, well, actually maybe Vadim might know, but Vera Gorbanova is not here. She'd know, but Vadim's been studying naked mole rats a little more.
Yeah, they are very slow to develop. Yeah, so I don't know exactly, but it's like a year they can reproduce. Much slower than mice.
Trying to turn some mice into naked mole rats.
Well, actually, yeah, it ties back to this neoteny that naked mole rats are neotenic rats, actually, because they look like little, when rats are just born, little rat pups, they look very similar to naked mole rats. They're also naked, and so this whole thing about like neoteny and like human are neotenic chimps, and this actually like slows down both the development but also prolongs lifespan. So to me, this all has very interconnected mechanisms that it would be nice to start untangling and actually pinpointing the genes rather than saying, yeah, it does like interconnect. Where exactly are those genes that are responsible for it? And can we just start playing around with them? Yes. Deigin.
So I would want to refine a little bit your question, because I think we agree that development is a program. Everything else may not be great. Yeah? So then we could slow development for various reasons. One reason, I mean, sexual maturity can be delayed for various reasons. One is just slower development and also wrong development. There's a so-called syndrome X in these girls, which are like 14-year-olds, they look like 2-year-old girls. And of course, they never live to 20, even to 20. Yeah, and yeah, so this may not work. I think this is a great idea that you proposed. It's just maybe, I don't know what's the ratio, 50-50. 50 would be completely different cases, but some might work.
Sure. Yeah, actually, yeah, the syndrome X is very interesting, and there is this case, this Australian person. He's actually lived to, still alive, he's 43, but he's exhibiting this like delayed or stalled development. He's essentially a child in there. He's 43 years old, but he's still a child. He's still alive. But yeah, there's obviously there's gotta be antagonistic pleiotropy between developmental genes and lifespan and survival. So actually if you kind of do break the development program, you're probably not it doesn't get you the fitness advantage that would actually let you survive. I think evolution kind of tuned that a long time ago. But yeah, I think it'd be really interesting to pinpoint, like, what are the genes that are responsible for the timings, because timings are so wildly different, and I think maybe finding out those genes could inform us maybe where to dig deeper for lifespan. So, any other questions or comments? No. Okay. Thank you so much.
Thank you. Wonderful. All right.